In this video, we're asked to compute the binding energy per nucleon for carbon-14 and express the answer in mega electron volts. We're given a table of reference values below. So the first thing in the list is the atomic mass unit in MeV per c squared. And I'll post a link to the video real quick where I discuss how to get MeV per c squared as a unit of mass if you're given kilograms. Next in the list, we have the mass of the carbon-14 atom. And that's the entire atom, including the electrons. That's a really important and subtle point that can cause problems when you're doing nuclear physics. And the tables that give you these masses, they always include the mass of the electrons in this number, and they express it in atomic mass units. This is why we have to have that conversion to MeV per c squared for the atomic mass unit. The next three in my list are the mass of the proton, neutron, and electron. And finally, we get a reminder of carbon's place in the periodic table, in particular, that the atomic number is 6. In other words, it has 6 protons in the nucleus. So we can write down the carbon-14 nuclide in our standard nuclide notation. The 6 is the number of protons, 14 total number of nucleons, and the 8 the number of neutrons. Now the whole idea with binding energy is that if I look at the mass of all the ingredients that go into an atom, it turns out to be greater than the mass of the atom itself. This is called the mass defect or the missing mass. And the reason we have a mass defect is that the nuclear potential energy goes down when these nucleons get stuck together. The strong forces snapping them together, potential energy is dropping. And we know from the famous equation E equals mc squared that when the energy goes down, the mass goes down. So this is what causes the net mass decrease of all these nucleons when a nucleus is formed from its raw ingredients. So the plan here is to compute the total mass defect when I compare the ingredients to the entire C-14 atom. And then we're going to find the energy equivalent of that missing mass. And then we're going to divide by the number of nucleons in the atom, and we'll have the binding energy per nucleon. So first, the ingredients. I have 6 protons, I have 8 neutrons, and I have 6 electrons. And again, even though we're doing nuclear physics, we have to include those electrons because what we're comparing to is the mass of an entire C-14 atom, including the electrons. So expressing all these masses in MeV per c squared, the numbers look like this. And this gives me a grand total of 13,149 MeV per c squared. Then I want to compare to the mass of the C-14 atom, but that's normally given to us in atomic mass units, so I have to do this little conversion. And the atomic mass units cancel out there, and I'll be left with the right units of MeV per c squared. And this gives me 13,043 MeV per c squared. So now I can compute how much mass is missing, or the mass defect. And this gives me 106 MeV per c squared. Remember, that's a unit of mass. So we still need to convert to a unit of energy here for the missing energy. And that's called the total binding energy for this nucleus. And that's given by E equals mc squared. In other words, we take the mass, and this is why these units are so convenient, the mass in MeV per c squared, and multiply by c squared, and the c squareds cancel, and I've got my total binding energy of 106 MeV. And then finally, I get my binding energy per nucleon. So this is just a way of comparing from one nucleus to another how tightly bound it is. You take that total binding energy and divide it up among how many nucleons there are. So in this case, I'm taking 106 MeV and dividing by the total number of nucleons, which was 14. And I get 7.57 MeV per nucleon. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.